Thank you. So let's begin with just like a very quick review of what we talked about last time, without going into any details. So the main point of the lecture last time was just to explain why the MHD splash problem is particularly interesting, especially in the 3D case. And we saw that the 2D problem was interesting in its own right, but I think you're going to see some things in 3 dimensions that you might miss out on if you only focus on 2D. So for example, right, we had a splash domain, and I can imagine the 2D picture or the 3D picture. And there's some magnetic field H in the exterior doing whatever. And then there's a B field in the interior, and there's a velocity field, but forget about that for now. The boundary conditions tell us that the B field and the H field, there might be some jump as I go from this magnetic field to this one across the boundary. But I do know that both fields are going to be tangent. So if I'm thinking about the 2D situation, one might wonder what the field lines of H are doing. And if they're tangent, perhaps they're doing something like this, right? As the splash is forming. And we saw before, maybe you'd be concerned if the field lines are getting more and more dense, that some enormous force is being created. But we saw through some heuristic argument that maybe that's not something to worry about. And another way why you might be relieved that that's not such a crazy singular scenario is that what really causes force is a flux of field lines. And yet in this picture, it's necessarily the case that every time a field line enters, the same field line has to exit, okay? That means that you expect the net flux is going to be 0. And so that's why even though the field lines are bunching together, the flux is not going to be, flux is going to be 0, just because everything is divergence free. And so yeah, so for the 2D picture, don't expect that there's some enormous force or something super degenerate. Well, degenerate maybe, but not super singular happening in between these two of the surface. But for 3D, it's potentially much more diverse what could be happening, because I could have field lines threading in and out of this as the splash is forming. So it's kind of mysterious what the H field looks like. And so for the first, I don't know, a third of this lecture, I kind of want to just focus on what the heck is H doing at the moment that a splash is happening. How do we solve for H when this is happening? So we have n dot H equals 0 on the boundary. H is going to solve this equation in the exterior only. It's only defined in the exterior. So obviously, if we have too many zeros here, the only H that solves the equation is going to be 0, right? So something just to keep in the back of your mind is that what we're allowed to do is impose some extra kind of boundary condition. Like maybe this whole picture is sitting inside of, I don't know, this isn't really a tokamak, but everything is inside of some enclosure, and you're allowed to prescribe something non-trivial. So in general, that's the kind of situation you're going to be looking at in order to have non-trivial H, because that's the interesting kind of magnetic fields for the splash, is when H is actually doing something in the exterior. But what we're going to focus on, because it's more or less equivalent, is solving this kind of problem where we just forget about the fact that everything is living inside of some chamber, okay? Because those problems are obviously related to each other, and it's going to simplify the discussion a little bit. So how do I solve for an H that gives me that? So it's kind of a standard strategy to propose that H is going to be the gradient of some function phi defined in the vacuum, where phi satisfies Laplacian of phi equals 0, and the normal derivative of phi equals g, on g. G may or may not have to have some kind of special conditions satisfied in order for this problem to be solvable. Okay, but anyways, there's sort of a standard practice of using layer potential theory to solve this when the surface is very nice. For example, if the surface obeys a chord arc condition, or basically just surface is smooth and non-self-intersecting, okay? So what happens to that theory when the surface is self-intersecting? That's what we've got to study here. Oh, and another caveat about the 3D picture versus the 2D picture is that in the 2D picture, we have the use of conformal changes of variables with which we can pry apart the splash, but have still some kind of divergence-free picture going on, because conformal maps give us an equivalent vector field which is divergence-free in the new coordinates as well, okay? For 3D, you have virtually no conformal maps compared to 2D. It's just far more constricted. So we're just going to solve it without opening it. That's the idea. And the way that we do that is we try to use the typical layer potential theory, which is where you take phi to be the single layer potential of some function f. That just means that essentially I have the solution is given by something like this, where this is a boundary integral. Let me call this domain omega. So there's a few key ideas here, but for the interesting self-intersecting picture, but at least for the non-self-intersecting picture, one finds that if phi is given by this, then on the boundary, you can take limits and calculate that dn phi, so the normal derivative on the surface, because this is giving us a harmonic function everywhere, except for that two-dimensional surface, is, call it 1/2 plus t star f, where t star f is given by the integral of, I'll write it as k of x minus y dot n of x against f. And there's a principal value in here. So we're going to be in a slightly different scenario, but we're going to use a couple key ideas to get as close as we can to this scenario. The first key idea is that, well, you're still going to find that this is true, right? But what you want to do is perhaps think about what happens when you, this is the whole boundary, but perhaps you can think of it as the union of various pieces. And if you focus on one piece at a time, you can deal with some surfaces which are not self-intersecting. Now they'll have boundary, for example, but we can still calculate limits and things in the same way. We can still verify identities like this. The fact that if I define the single layer potential in this way, and I calculate what the normal derivative is, this formula still works for a self-intersecting surface. I can verify that by just kind of looking at pieces of the domain and then verify it in the standard way for a non-self-intersecting surface. Right, so key ideas. For example, we can decompose 1/2. Okay, I'm going to use sort of a strange notation here. So if I were just integrating over the top piece, so that's sort of the notation I'll use for that. This is the same thing as taking the normal derivative of integral of the the single layer potential over just this piece. Okay? That's essentially because F here. I could do this calculation for an F which is only supported on the top half, and then this would be the standard calculation. Another key idea is that the integral over the other piece is sort of like a reflection in some sense. It definitely involves reflection of the integral over the top piece. Okay? Somehow this is going to show us why there's some degeneracy here, right? Maybe I should actually say a couple more words about the degeneracy. So one reason why you expect there to be a degeneracy here for the self-intersecting surface is that it's calculating the normal derivative of a harmonic function in the exterior, and we're assuming symmetry everywhere. That's another important point. So we have some sort of symmetry in the vertical coordinate, meaning that every time there's an h pointing up in the bottom region, there's an equivalent h pointing down in the top region. H is the gradient of a harmonic function. That's the same thing as saying that phi, that harmonic function, is even. And if I'm computing the normal derivative at the point of the splash and everything's even, by necessity, more or less, that normal derivative is going to have to be 0. Even if the f's that I'm plugging in here are non-trivial. They, in fact, could be concentrating near the splash point with some L2 norm that's strictly bounded below, greater than 1 or something like that. Yet we would still expect that this formula is going to be returning something that's getting smaller and smaller. And so we're going to see where that degeneracy comes by observing that there's some sort of reflection symmetry coupled with a normal that's pointing the opposite way as the normal coming from the top. So I think I'm just going to give some heuristics for this because the actual calculations are a little bit messy. Okay, also I'm going to only consider F supported near the splash point. That's basically because if you want to deal with F that has non-trivial mass elsewhere, it's just going to kind of, you have to verify a lot of things, but it's going to, the kinds of estimates that you do are going to be the same as the types of estimates you do for non-self-intersecting surfaces, okay? Let's just focus on F supported near the splash point. And so I'm going to kind of ignore integrals over the neck of the splash, okay? And because this is what really contributes, what really matters for this problem. The neck of the domain. By that I just mean the bridge that kind of connects the top piece from the bottom piece. Okay, so let's ask, what does this operator look like? So here I'm just looking at the single layer potential for a self-intersecting surface, but I'm just looking at the two humps touching each other. I've ignored the majority of the surface. I'm just focusing on operator acting on stuff supported near the splash point. And I'm going to take advantage of this property. So I'm going to say this is equal to integral, well, 1/2 the identity plus the integral. Oh, I should also plug in a particular x just to make a little bit better sense of this. So let's pick an f and specify the x that we're looking at. Just decomposing the integral in terms of an integral over the top bump and an integral over the bottom bump. Now, I'm going to look at an x on the top hump. Here, right? Now I'm going to use this idea, the fact that the integral over the bottom is kind of a reflection in some sense of an integral over the top. Use some symmetries in the kernel. So this is actually going to be equal to integral over the top of f of rx. So this is the reflection of x in the plane, right? So if I have x here, rx here, okay? If I have n here, I have rn here. So more or less, you're just going to get the equivalent thing, but the reflected version, okay? Again, we're just being heuristic here. But now, the point is that this guy is equal to the normal derivative of the single layer potential associated to the top hump, right? Just by standard single layer potential stuff, right? We don't even have to acknowledge the fact that the surface is self-intersecting to make that calculation. Is n of integral over the top hump. And I can verify that actually this guy is similar. Okay? This guy is going to be what I would get. You have to check this. But he's also going to look like a derivative of an integral of this form. And in fact, what it is what you would get if you took the single layer potential associated to the top, and then you evaluated the field, so we get a harmonic function coming off of that, right? And I'm thinking about what it's doing outside, and I'm actually going to calculate the normal derivative of that field in the exterior at this point, Rx, in the direction Rn. So if you're careful and you think about it, you realize that this guy, if he's this, is Rn of the same integral over the top. Here I'm going to have to write x tilde, and then I evaluate it at x tilde equals Rx, the reflection of x. Okay? And so the reason we're doing all this is to somehow massage the operator and kind of write it in terms of an operator that we know and understand, and that is the single layer potential associated to a non-self-intersecting surface. That's what this guy is, right? You kind of play this game of adding and subtracting a couple terms, and now you have this key understandable piece on the inside, which is this well understood single layer potential. And you just kind of factor the operators. So there's another anti-symmetry that you're going to take advantage of here. And it's the fact that as I go closer and closer to the splash, x and rx are kind of canceling, right? So there's another degeneracy potentially here. So if n is, well, let's just be rough. N is essentially x minus 1, and Rn is x plus 1. So notice that means that n plus Rn is 2x 0. Right? I'm going to kind of use that over here, and I'm going to add and subtract drn, and then I'm going to use the fact that in front of some terms I'm going to have this guy. It's going to become 2x dot gradient. So you just kind of add and subtract and commute a couple of these operators. So, I mean, we don't necessarily need to go over all the details, but play with it a little bit. Commute, so that's you can't really commute these, right? This is very rough approximation. Like I can't commute, if this is a single layer potential, and here I have some derivative that depends on where I am with respect to x, I can't commute anything like that. But I can keep track of the error if I kind of do things very carefully for functions supported in a tiny neighborhood of this, okay? And the way that you can do that is by using like just very basic pseudo-differential stuff where you write everything, all the kernels down in terms of their Fourier transforms, and you evaluate along the curve, and you can make it work. You can make it rigorous and keep track of the errors that you get when you commute these operators. But let's not worry about that. Let's just kind of fudge it. So I'll tell you, there's a couple other key pieces that you need to get the end product you want. So drn is going to be more or less a normal derivative of a harmonic function coming off of a relatively flat surface. Okay? So drn is basically going to be like lambda, square root of minus Laplacian, because that's how you leap off of a flat surface, right? That's how you calculate the normal derivative of a harmonic function. And again, that's a very rough approximation because Rn is actually not pointing directly normal. It's only normal at the splash point, but forget about that. There's this other piece, which is the fact that you have a single layer potential here, but you're evaluating it at Rx, not x, right? The other key operator kind of floating around is if you have a harmonic function kind of coming off of the surface, you want to evaluate the harmonic function here at Rx. Operator that kind of converts your trace of a harmonic function on this surface to a trace of a harmonic function on this surface is going to be given more or less by the Poisson transform. Okay? So it's similar to a situation where you have the trace of a harmonic function on a plane. Okay? And you have a paraboloid. And if you have harmonic phi here, and you want to calculate the extension from the data on the plane, let's say you travel a distance of minus x squared, right? Well, we all know that operator, right? The operator that tells us how to calculate the how a harmonic function leaps off of a flat surface, right? It's given by this operator, e to the minus x squared. And that's because the surface is given by x squared, okay? Now this is a very rough heuristic, but you end up getting basically the same thing in this picture. In particular, if f is just supported in a tiny neighborhood of this point. Let's say this top surface is roughly plus x squared over 2, and the bottom surface is minus x squared over 2. Again, you're going to find that the way that this harmonic function, the single layer potential, leaps off of the top surface is roughly given by this operator. So the thing that you basically learn is that the integral over the top of 1 over x minus y, f of y, but in the case that you say, let's evaluate it at, well, we'll put an x tilde, at x tilde equals rx, is more or less like this operator applied to the other guy, where I've just evaluated it at x instead of rx. Okay? So that's the other piece that I'm going to use to kind of factor these operators. So again, you keep this in mind when you're trying to make sense of this guy, and you just kind of add and subtract and keep track of things like this is going to happen as well. Okay? Long story short, arrive at an operator which looks like let's write it from the start. 1/2 plus t star associated to these two touching waves is more or less like, well, let's even forget about the fact that we're evaluating at f. This operator is more or less like I'll just tell you the answer because there's other things to discuss, but basically you get something like this. 2x dotted with the gradient plus x squared times the Laplacian. And then here you end up having something having to do with this operator and the fact that sometimes we're evaluating the harmonic function on the top surface, but it's going to be next to a normal pointing down, and that's going to look like minus the identity, -1. And sometimes I'm going to be evaluating something on the bottom surface. It's something that's just morally like this, okay? The idea being that I've kind of factored, so this naturally was appearing, right? The evaluation on the top piece minus the evaluation on the bottom piece. And if I were to say make a Taylor series for e to the minus x squared lambda, I would, not a crazy thing to try to factor that term out. That means that I'm going to pick it up somewhere in here, but it's going to be next to a normal derivative, which gives me another lambda. So I essentially factored out an x squared lambda and applied lambda, and up to, I don't know which way I'm commuting things, but I hope you'll believe me when I say that that gives you something like x squared times the Laplacian, roughly. And of course, on the right, I have this integral. But this is the more interesting. And the point is that it's not exactly this because we made so many simplifications, so many commutations and things, but something which is morally behaving like this, okay? And this is something which you can roughly invert with pseudo-differential calculus, at least up to a smooth error. But that's a bit too technical to talk about. This piece is positive. So by that I mean that it satisfies, let's write it this way, x squared Laplacian plus 2x dot grad f, even though it's obviously degenerate with the x out in front, so we can see how everything is vanishing when x is 0. This actually obeys this inequality on L2. It's bounded below by the L2 norm of f with constant 1. Initially is kind of surprising because the operator is vanishing, right? But if you just play around with an integration by parts argument, and you do a couple clever tricks, you can verify that this is true with constant 1. Okay? So that's a good thing to check. It's not a trivial thing, but and you can use pseudo-differential calculus to deal with this guy. This guy looks like a single layer potential for a non-self-intersecting shape, which is going to look like roughly like 1 over lambda, maybe 1 over 2 lambda. And put all this together and you learn that this operator is bounded below. But you find that you do lose some derivatives from these extra more complicated pieces. You learn that 1/2 plus t star f, f supported in a tiny neighborhood of that point, greater than or equal to, well, we have a non-trivial constant here, but you actually lose 2 derivatives in the sense that it seems you can only bound it below by the h minus 2 norm. So this is saying that it's degenerate, but it's not so degenerate that you can't find some lower bound in some space, right? And that's critical for coming up with an inverse. So I don't want to get into the details on how you use this type of lower bound to invert the operator, but I think at least it's plausible that proving a lower bound is the first step to proving something is not hopelessly degenerate, right? You can say that, yes, if I plug in functions concentrating near the splash point, things could be going to zero, but at least they're going to zero no faster than some concrete, I guess it's a more generous norm than the L2 norm. So it allows us to deal with that. So this basically just concludes what I wanted to say about how to solve for H. But I'll just say that once you use this to solve for H, that's a huge part of the problem. And the same ideas allow you to solve for the interior Dirichlet problem. And that's because there's this really tight link between the interior Dirichlet problem and the exterior Neumann problem. Because the interior Dirichlet is dealing with this, and this is going to be the adjoint of the other problem. At least I hope you believe me in terms of just taking duals of things and looking at, you know, the dual picture. If you can invert one, morally speaking, you ought to be able to invert the other. Okay? That allows you to solve the interior Dirichlet problem. So does anyone have any questions about this? This is kind of an encapsulated, it's a bit separate from what we're going to talk about next. But I hope it was, I couldn't go over the details, but I hope it was a little bit intuitive at least. So far so good? Or? Okay. Well, let's just go to the next thing then. So now I just want to talk about mostly stuff going on in the interior for a minute. Okay, because we haven't even written down the MHD equations so far. So what we're going to do is use the Cauchy-Kovalevskaya theorems to prove that we have some sort of analytic existence of an analytic function. And we have the equations for the plasma in the interior, which are given by this for the velocity field, where B is this interior B field. The B field satisfies this equation. And we have divergence free of both fields. And we have some conditions on the boundary, of course. So on the boundary, B dot n equals 0, and P evaluated on the boundary is given by 1/2 the magnitude of H squared. Right, and so the goal is to use Cauchy-Kovalevskaya. It is CK type theorem, prove local existence. In analytic spaces. And so basically the way you can do this is you just kind of count, well, in general, to do this, you just count derivatives. So one time derivative in left hand side, you want that equated to one space derivative in some sense. So you're allowed to get creative as to what it means to have one space derivative in the right-hand side. Like you could have all kinds of crazy integrations and various kernels and things, but in some sense, you're going to want to verify that the spatial regularity of the right-hand side can only get worse by 1 degree, given the thing that you're putting in, has a certain, say, Sobolev regularity. This is the general idea here. And also, you just have to make sense of, having various complexified parameters, maybe complexified variables as they appear in the system. Okay. So speaking of that, making sense of the complexification, I think it's relevant to give a minute to talk about the domain that we work with. So before I was drawing kind of a simply connected blob, but for one reason or another, we decided to work with a domain that looks more like this, so a torus. And one nice thing about this is that I guess maybe this is what's going on inside of a tokamak. Honestly, I have no idea if the plasma itself forms a torus. But for whatever reason, it was more convenient for us to prove things in terms of toroidal domain anyways. So let's deal with the torus. And it's actually a solid torus. It's not just an equation on the boundary. So I have 3 parameters. Let's say that, one of these is my phi variable. Maybe I'll draw it this way. So this long way around, maybe that's phi. Maybe this way around, I'll say theta. But then I've also got some sort of thickness parameter, which I'll call rho, right? So every rho slice is kind of a nested torus, right? I'm allowed to describe things in terms of these variables. And I'm going to have some function x of, I'll write it as x of alpha rho t. And this is going to be vectory. But it's also just going to map out the plasma. So if I put x of alpha t at t equals 0, that's going to map out the initial shape of the torus. So it's like saying this is a function. There could be some degeneracies at rho near 0, but let's not worry about that too much. Maybe think of it as though up here is rho equals 0, and then here I have some sort of periodicity corresponding to maybe this direction corresponds to this, and maybe this direction corresponds to this, right? So one of these could be alpha 1, one of these could be alpha 2, this could be rho, this kind of picture, where it's like a torus crossed with a line segment, okay? This is the domain of this function. At time t equals 0, it maps to the initial torus, and then at later times, it tracks where each of those starting points was, and it spits out the final terminating point. And the reason why I bring this up at this point is that for one reason or another, it's easier to complexify variables in a torus, just a 2-dimensional torus, than it is in a manifold with a boundary. This is a very technical point, but it's just, frankly, kind of a pain in the butt to figure out what does it mean for it to be analytic in the normal direction at the boundary. Because in theory, if you were analytic on the boundary in that direction, you would have some sort of extension, so you could expand the domain out a little bit more. And then you have to ask yourself, well, is my boundary the boundary that I had before the extension, or the boundary after I had the extension? So very technical. Perhaps it can be dealt with, but for whatever reason, it was much easier for us to just complexify in the tangential direction And I mean, I think you see this in plenty of other areas of fluids, where if you can make the problem lower dimensional, then you've made huge strides in making the problem easier, okay? It looks like we're having to do the problem over a whole solid torus, not just the boundary. The reason why that's different from something like water wave is because you can't require that the curl is zero. So for water wave, there's a key difference from water wave. So can't assume curl is zero. And the reason for that is that the vorticity equation is more complicated in this picture. For water wave, if I took the curl of this equation, I would not see this term. And I would find the standard vorticity equation, which incidentally actually looks like this equation for B. Okay? Verify that. And if you look at the equation, it looks like this. So I'll just write a little box here because it doesn't apply to our scenario. You can think of this as saying that the transport of the vorticity is proportional to the vorticity, and then you have this other relevant factor, but key point is that it's proportional to the vorticity itself. So you could imagine perhaps you're trying to calculate the vorticity as an evolution along a curve. And so if it's initially if it's initially zero, you don't get an initial kick. Like pretend you're solving for the vorticity using the method of characteristics, right? If you're trying to do that, you would discover that if it's initially zero, it's zero along the trajectory forever. Okay. And why that's relevant is that for water wave, you know that you can just take vorticity to be zero, and that allows you to make the problem lower dimensional, okay? And I don't have too much time to discuss that in detail, but the point is that you can recover the velocities from a Biot-Savart integral, and you can think of it as though, well, okay, I could say the curl is zero, but I could also say the curl is given by a measure which is supported on the surface. When I calculate the velocities from the Biot-Savart law, I'm calculating an integral over a surface. Well, okay, that's good because now I'm just focusing on the evolution of the surface. And I can calculate all the other unknowns everywhere else in the problem just from the dynamics on the surface. That all comes from the fact that the curl can be assumed to be zero. So the way that this is related to what I was discussing here is that we would really love to make the problem as two-dimensional as we can for various reasons. So in particular, because it's difficult to make sense of, at least harder to make sense of analyticity in the normal direction, in the row direction. So how can we do that? Okay, so how make our problem as 2D as possible? To make life easier. And to explain how to do this, I'm going to use a general fact, which is that, maybe I'm getting ahead of myself a little bit, but in general, for a divergence-free vector field, if you know that it's divergence-free, and you know the tangential derivative of that vector field, or the various tangential derivatives if it's higher dimensions, you can calculate the normal derivative, so the derivative in the direction normal to those two tangents, terms of the curl and those other derivatives. What does that mean? So arguing that D normal divergence-free vector field can be computed from D tan of stuff and the curl of the function. And what's really going on here is just counting the number of degrees of freedom, right? You could think of, okay, I have this vector field, I have the gradient of it. This is forming like a, say, a 3 by 3 matrix. If I fix the divergence, you know, I'm imposing one constraint on that system. And then if I'm trying to calculate the normal derivative, you know, you just count the degrees of freedom. But a nice way to see this in 2 dimensions, for example, that Cauchy-Riemann equations tell you precisely how to calculate the normal derivative. So if you have a holomorphic function, you can, so this is just 2D for this heuristic. You want to calculate the normal derivative of that vector field here. You can determine it completely from the derivative in that direction. It's just going to be determined by like multiplication by I or something like that. But holomorphic functions are analogous to things that are both curl-free and divergence-free. That's the Cauchy-Riemann equations, right? So the point is that if you know that, say, the divergence is free, but the curl is not free, you get a little error in your formula for how to calculate the other derivative. But if you actually go through the math, you find that that error is trackable. So you can calculate what the actual derivative in this direction is. So it's basically the same thing in 3D, but visualize it in 2D more easily. The proof is just counting the number of degrees of freedom. So the point of this is that hopefully we can use such a relation because we have so many divergence free fields flying around that maybe every time we see a normal derivative hiding in here, we can replace it with something having to do with the tangential derivatives and the curl. And then we try to track the curl because we'll still have to, that's the price we pay. We trade normal derivatives for tangential derivatives at the price of introducing the curl. So if we're going to do this, we have to understand the evolution of the curl. So if you take the curl of those equations, you get I'll write omega to be the curl of U, and capital J is going to be the curl of B. So what we find is that, also I'm just going to write capital D to indicate the material derivative or the transport. You find just by taking the curl of those two equations that dt omega is equal to omega dot grad U plus E dot grad J minus J dot grad B. Okay. And then for J, I end up getting dtj equals J dot grad U plus E dot grad omega, messy, omega dot grad B, and then I have this mess, minus 2 times the sum over I from 1 to 3 of gradient of ui crossed with gradient of bi. So the details aren't really important there. But what we should really be looking at is where are we forced to deal with normal derivatives, right? What we just observed is that if I want to replace normal derivatives, or let's say row derivatives, with tangential derivatives, I'm sort of free to do that in these equations, just because I've introduced the curl now, right? So I can use my formula write every time a normal derivative appears in terms of the tangential derivative and the curl. By introducing omega and j as new unknowns, I can just plug stuff into this formula, and there are now no more normal derivatives except for perhaps the pressure. Let's ignore the pressure for now. But where B appears and where U appears, I'm fine. Now I have to look at the evolutions of omega and j. And, well, every time I see gradient U or gradient B, I can use my formula that I just developed to introduce tangential derivatives and then new appearances of j and new appearances of omega, right? But I still have to deal with, for example, the case where higher derivatives fall on j and higher derivatives fall on omega. The only time that happens is when it gets hit by b. So perhaps if we can tame b, then we know what's going on. So we're going to pick special b to make things work. The reason that we can sort of pick a special b to make things work is that the evolution of b is pretty simple. So if you look at the original equation, you'll notice that the equation for b is the same as the equation for the vorticity for standard Euler. And if you check, you'll find that actually it means that if I take b and I evaluate it along a trajectory, let's say of a t, where a is alpha rho, it's actually given by b0, alpha x of a 0, plotted into the gradient of x. So essentially what this is saying is that I can set up my initial variables or my initial b field so that b is always pointing in a good direction. That the derivatives that I get here and here are aligned with something, let's say d alpha 1x and d alpha 2x. I take my initial data so that these are actually tangential derivatives, and then I'm fine. And I'm free to do that because the evolution of b is so simple. It's just a matter of prescribing the initial data, and then the magic of the MHD equations is that things are kind of frozen, they say, along the trajectories, and that property will persist at later times. So that's great because that means that we can completely replace this system by one in which only tangential derivatives are appearing. But that seems almost too good to be true, right? Because clearly the equation shouldn't completely decouple. Rho has some dependence, right? There's got to be some coupling between the dynamics on this thin tube in the center, right, and say the tube on the outside. So where did the rho dependence go? And the answer is that the rho dependence is in the thing we ignored, which is the pressure. So we have some sort of decoupling, but really the rho dependence is there. It's just that it's hidden in the pressure. Maybe I'll just say a few words about that because how much time do I have left? We started a little bit late, right? 5 minutes. Okay. So I'll just say a few words about this. It's in the pressure, but the pressure can be recovered from the other things in the system. Okay. So you can actually take the divergence of this equation, get kind of a natural equation for the pressure. It's sort of a standard practice. And I may not get the signs right, but I think what you end up getting is something like the trace of the matrix gradient of u squared minus gradient of b squared. Maybe the sign is flipped. Calculate the divergence, and then you use, some divergence-free properties of things. This is what it boils down to. Then you just want to write naively p equals Laplace inverse of right-hand side, where by this I just mean the stupid thing, which is to write it as this integral. Well, the oversimplification. 1 over x minus y. This is a volume integral over omega of this quadratic function of gradient u, gradient b. So it's a volume integral, and that means that I'm integrating over rho. Okay? But I'm just going to write this in terms of the various unknowns in the system. So I can write this as an integral over the torus crossed with rho, right? So 0 to 1, something like this. X of a t minus x. If I evaluate it at the point x of a t, here I would have grad u tilde, grad b tilde, determinate. So this would be, I would pick up a Jacobian by substituting y equals x of bt. Something like this, where the tilde indicates, for example, b tilde equals b of x of a. I guess in this case it's x of bt, but I've chosen the unfortunate notation where my integration variable is the same as one of the unknowns in the problem, but so the rho dependence appears, but only in the integration. So it's very weak. And so you can kind of see how, given all of this, oh, I did cheat a little bit because I completely ignored the boundary condition. So what I need to do is add like a harmonic correction, which solves the necessary Dirichlet problem. But that's what we were learning how to solve in the first quarter of the, right on the corrector. So, but once you've done that, you can see that it essentially works out that the number of derivatives in the right-hand side is not greater than it needs to be, and the rho dependence doesn't disappear, but it only enters in a very weak way, which is very well suited to a Cauchy-Kovalevskaya type theorem. Now I'm integrating over various knowns, but I'm allowed to do that. It's just more of an abstract function in the right-hand side. That's all I have to say about that, I suppose. Yes, although, well, okay, so there's an interesting point here. Yes. So an interesting thing is that it's not terribly difficult to find a good B naught. So that you just need B naught to be divergence free. And that's because I did not say anything to specify the initial map X of alpha rho. So what I would like to do is choose any way of foliating this thick torus. That's going to be what I'm going to use to, well, either pick my B field or just see what types of B fields might work. So I would like to take a B field that looks something like this, or maybe some very simple other version, right, throughout the tube. The reason why that's not unbelievable that such a thing should work is that the divergence should be 0 as long as the flux doesn't depend on the area integral that I take. Yeah, so you just take a B field like this, and then you just say, I'm going to create my initial parameterization of the domain is going to be determined by that B field that I chose. So I just choose it so that the tangent vectors line up, basically. There's another interesting point about this, but I don't have a whole lot of, maybe just say a quick brief thing about this. So another thing is that, okay, so really the splash looks something like this, right? Because we're doing a torus. And you also need to check that the B field that you choose, which way it's going, but just that it allows for this separation to occur because you're going to take advantage of those extra forces to open the splash. Yes. So the key non-trivial part of that, so one reason for that is that I was left with the single layer potential, and that's going to force me to have like a 1 over lambda in there. The other thing is that I had this weird operator 1 minus e to the, this type of thing, morally speaking, but in practice it's more complicated. So this is not an elliptic operator, strictly speaking. For example, the point is you're gonna have operators popping up, pseudo-differential operators that are not elliptic. You have to invert them, but you don't gain back every derivative that you expended when you invert them.